Hello students, welcome to the channel Statistica Hub. So we were discussing GATE statistics paper from the year 2024. So in the last lecture, we discussed the problem number 11 and 12. So in this video, we are going to cover problem number 13 and 14. So if you're struggling with problem 11 and 12, just go and watch that video. So in this video, I will take through the problem number 13 first. So in the 13 problem, whatever is given, let's try to understand that point of view. So we are given that A is some matrix of order 3 cross 3, and it is given, it is a real matrix. Okay, so whatever information is given, you have to utilize that thing. Okay, then we are given that I3, that is an identity matrix of order 3 cross 3 identity matrix. Okay, now we have to find which of the following statement is not true. Okay, so first, like whenever you solve the problems or whenever you just see the problems in the exam, just focus on what is being asked. In this problem, you have to find the statement which is not true. So you have to find the statement that is false. That's it. Okay, so if we go for the first statement, then the statement number A, that is saying that if the row echelon form of the matrix A is I3, so we are given that the row echelon form of A is I3, then 0 is not an eigen value of A. Okay, so for this concept, like you have to understand a little bit about the linear algebra, not little bit, like a little bit focused way. Okay, so in this problem, as it is given that the row echelon form is coming out to be I3, this implies that the matrix A is invertible. So if the matrix A is invertible, then this implies that the invertible matrix don't have 0 as the eigenvalue. So this implies that 0 is not an eigenvalue. So you didn't have to solve the problem. You just like, this is a theoretical problem. You just have to focus on what is written and what we can conclude. So the statement A, that is making some sense. So this is a correct option. This is true. We have to find the false one. This is true. Move to the statement number B. So the B statement is saying that if 0 is not an eigenvalue of A, then the row echelon form of A is I3. Okay, so you can see it is just the converse of the above statement, like slightly just converse of the above statement. So for that statement, I will go for something about the logics first. So in the logics, you may have understood this one thing, that if A implies B, then we can't say that B implies A. You can't say this thing, but we can make sure that not B implies not A. This is true. Okay, but in this particular setup, what is something that is something like we have to focus on? So this statement that is given in this particular thing, that we are having that 0 is not an eigenvalue, this implies that A is invertible. Okay, we can just conclude from the part A also. So this is the converse statement. Now this will be holding in this particular situation because we are given a finite dimension space. So the finite dimension space that is given to be R3. So in this particular situation, the inverse also holds. So the statement B, that is also true. So I can simply write this statement is also true. Okay, move to the statement C. So if A has 3 distinct eigenvalues, then the row echelon form of A is I3. Okay, so in this problem, the things are like very straightforward. So I can simply go for the part C. So C, you can simply see that we are having some equation like lambda minus 1, lambda minus 2, that is coming out to be 0. So from this particular equation, I can simply conclude that, like this is for example. So I can conclude that lambda is coming out to be 0, lambda is coming out to be 1, lambda is coming out to be 2. So what we can see, we are having distinct eigenvalues. But in this particular setup, the matrix A is non-invertible. Okay, so if the matrix is non-invertible, then we can't say that the row echelon form that will form the row reduced echelon form that will form I3. So this statement is something that is false. Okay, so this is something that is false. So the C, that will be the correct option in this one. Okay, let's try to see the last one also. So in the D, it is saying that if the system of equation AX equal to B has a solution for every 3 to 1 real column vector B, Then the row reduced echelon. Okay, now this is again very simple problem. The statement D, that is straightforward again. So in the D, they are saying that the system of equation Ax equal to B has solution for all vector B, the column vector. I'm not writing the complete statement. So from this particular situation, I can simply see that the X that will be A inverse B. So that means to say the matrix A is invertible. And if the matrix A is invertible, the row reduced form, that will come out to be I3. Okay, a very basic problem, completely definition based problem, nothing new. Okay, moving to the next problem. Okay, again a linear algebra problem. There are a lot of linear linear algebra. Okay, so let's try to see this problem. So in this one, we are given that you are having. So we are given that u1, u2, u3, okay, v1, v2. Okay, so you are given u1, u2, u3. These are some vectors that belong to R4. Then we are having v1, v2, v3. These belong to the R4 again. And u is span of u1, u2, u3. Okay, v is span of v1, v2, v3. Then we are given some of the statements. Let's try to see these statements. Okay, so the first statement says that if the dimension of u intersection v, that is coming out to be 2, then the dimension of u, that is 3, then these are linearly dependent. Okay, so I think this is wrong. So if I go for the statement number 1, then according to the statement, let me write the statement. Okay, so we are given u intersection v is having a dimension that is coming out to be 2, and the dimension of u that is given to be 3. And then they are saying that then the vector v1, v2, v3 are linearly dependent. Okay, let's try to see this problem. So suppose that we are having the span that is given. So suppose that u and v are subspecies of, they are some subspecies of R4. Okay, and we know what is u, that is the span given by the u1, u2, u3, and v, that is the span given by v1, v2, v3. Okay, now say u1 vector that is exactly equal to the v1, because there was nothing given about these vectors, and u2 is exactly equal to the v2, and the u3 that is not equal to the v3. Okay, now if v3 is, we can just make some statement about v3. So let's say v3 is such that it is linearly independent of v1 and v2. Okay, then the v1, v2, and v3 are linearly independent. So the statement that was given, that is false. That is not holding any situation in this part. So you can simply see, according to the statement, whatever was given, it was given that the dimension of u intersection v that was given to be 2, and the dimension of u that is given to be 3. But we got some vector v1, v2, v3, which is linearly independent. And we were supposed to check that they are coming out to be linearly dependent. Okay, that makes sense. Okay, the dimension role that and the dimensional role that have been played in these examples, you can just cross check that thing. Okay, moving to the second statement. So if I go for the other statement, then it is given that, okay, if u plus v equal to u plus v, such that this equal to R4. So you can simply see in the part B that if you add these two things, then you are getting R4, the complete vector space of R4. Now, either this vector is linearly independent or the other vectors, they are coming out to be linearly independent. Okay, this one also feel to be incorrect. So let's try to frame like one counter example. So if we go for this problem, the B part or the B statement or the second statement, whatever was given. So you are given u plus v, that is coming out to be u plus v. I'm not writing everything, and that is simply coming out to be the R4. Okay, so this means to say that the combined span of vectors in u and v covers the complete R4. Okay, now let's try to frame one example, the counter example you can say. So the counter example that can be something like this. Let's say okay, so let's say that we are having the u1 vector. You can frame it to be like that was of the dimension 4, right? R4. So you can simply say this is 0, 0, 0. Then you can take the u2 vector that is 0, 1, 0, 0. Now I can frame the u3 that will be coming out to be 1, 1, 0, 0. So you can simply see this is linearly dependent on these two. Okay, moving ahead, you can go for the V1. In the similar sense, you can define them, or you can define in other sense also. V2, you can consider 0, 0, 0, and 1. And finally, you can go for the V3 as a linear combination. So I can say 0, 0, 1, 1. So this is again coming out to be linearly dependent of these two vectors. Okay, so what we are getting that both of them, we just proved that both of them are coming out to be linearly dependent. So in this particular setup or in this particular statement, they are saying that they are linearly independent. So this is also false. So both the statements are coming out to be false. So the correct option will be D. So this was all about problem number 13 and 14. I hope you are able to understand the problems. Stay tuned to the channel. More videos are coming soon. Thank you.